What would you do if you hired somebody to do a particular job and not only would they deliver it well past the promised deadline, but when they would finally deliver it, it would be a far cry from the expected quality and nowhere near the standard that you agreed to pay for in the first place? Well, you probably would let them go. As you might have noticed by the tone of my voice in the intro, we're going to start this month's update in a bit more of a negative light. You see, the company that we hired to help us speed up our routing efforts actually ended up slowing them down. Not intentionally, mind you, I just think they underestimated the amount of work needed to get it done. Now, combine that with their poor communication skills and you have a recipe for, let's say, not the most pleasant cooperating experience. Now, if you missed my previous update video in which I explained our plans to hire external help with the PCB, here's a short recap. Towards the end of August, we realized we're a bit short-staffed for the amount of work needed to be done to get the PCB from schematics, which is the point we were at the time, and all the way to the finished PCB, which is where we were hoping to get at the end of September or early October. Well, clearly that didn't happen, and the mistake we did was not realizing we're going in the wrong direction early enough. You see, Altium, the software that we use to design our PCB, has a cloud component that allows everyone on the team to see what has been done, or more importantly, how much and when. And about 2 weeks into this cooperation, things haven't moved much, but we didn't panic just yet, because we knew there is some homework necessary to understand how things fit together on the schematic, especially for an outsider. Our worst fears started to materialize only when we saw that another week in, so the third week of their work, things did start to move, but not nearly as fast as we were hoping, and at that moment we knew things were going to get delayed. After a meeting with them, they asked for a 14-day extension, and we really had no choice but to agree to it, hoping things would turn around. Well, they didn't, and a week into this extension, we had a call with them and told them that we're going to take care of the board ourselves, even if that meant that Aljaž and Ken would have to work insane extra hours to get us to where we are today. Now, of course, there had to be repercussions for the lost time, so we offered to pay 4K instead of initially agreed 9, which they reluctantly accepted, and we parted ways. By the way, if you're new here and don't know who Aljaž and Ken are, Aljaž is my co-founder and is an electro-technical engineer, and Ken is his former co-worker who helps us out in his spare time. And no, I'm not going to name names here regarding the company we worked with, because the game theory says you should be kind and forgiving, but not too forgiving, and after all, they did deliver some value, and I think the reduction in price was fair enough for them to hopefully learn from this and take a different approach going forward. And as for the consequences on our side, beside the lost time that is, I should also mention another more practical casualty of these shenanigans, and those are the M.2 ports. If you followed my videos for any length of time, then you know that our board also has two M.2 connections on the bottom, and we decided that in order for the prototypes to go into the manufacturing phase as fast as possible, we are going to leave them unconnected until the next round of prototyping. Now that the bad news is out of the way, let's look at the PCB, which is now significantly different from the one that you've seen in my previous update. Not only because Aljaž and Ken took over, but also because the design studio that we're working with also had some feedback. Primarily about the stuff that revolves around mechanical properties and mounting, so let's look at those changes first. The first thing we did was move all the connectors from one side of the board to the other, not only because it makes sense from a user experience point of view, but because we've looked at a ton of rack-mountable networking gear and pretty much all of them align their ports to the right-hand side of the front panel, and as such it made sense to move all the connectors onto the side that will be more easily accessible both when assembling the device as well as any possible maintenance down the line. Next, we've added some indentations to the left edge of the PCB, namely this one here next to the auxiliary power connector and this one on the top left corner. We did this because in the Founders Edition enclosure, the PCB will be mounted slightly off-center and it's purely for aesthetic reasons. You see how on the side with the USB ports, the edge of the left mount USB-C connector is further away from the edge of the PCB than the SFP cage that is on the right side? Now, obviously, you won't be able to tell this once the PCB is mounted into the case, but what you would be able to tell almost instantly is that something is off if the port on the right was closer to the edge of the device than the port on the left. And to solve that issue, we decided to mount the PCB slightly to the side, which resulted in it clashing with the case mounting holes. Now, the easier solution would be just to make the case bigger and move the mounting holes further apart, but since we want to make the device smaller rather than larger, we decided that these two cutouts are the way to go. And while we're talking about mounting, let's also mention these two standoffs. You see, in the previous iteration, we just had normal mounting holes here, but discovered that this one in particular would be pretty much impossible to align with a standoff that was initially planned to be part of the enclosure. And the reason for this is how we will assemble the two. You see, due to the shape of the enclosure, which I'm not going to show you just yet, we need to slide the PCB into it at an angle, and because of the height of the surrounding components, namely the magnetics and the RJ45 port, the standoff, if it was a part of the enclosure, simply wouldn't fit. So what we did was we removed the standoff from the case and instead added it to the PCB itself. And the same goes for the other hole that's close to the USB ports. But with that one, we're solving another problem, and that's the fact that we'll be using undercuts, and to manufacture those undercuts, we'll need a special T-shaped drill bits. Here's a basic drawing as how that process looks like. You have a wall of the enclosure on which you want to create an undercut, and to be able to do so, you need a tool that has a cutting edge that is wider than its shaft, which results in these kind of tools being relatively large and bulky. And if we wanted a standoff here, it would have to be a separate piece, which would also have to be manufactured separately. Well, luckily for us, we already found the solution for the inner mounting hole, and that same solution turned out to be applicable to the outer hole as well. Win-win. Okay, now that we've looked at mechanical properties of the PCB, let's go over the electricals ones as well and talk about how the chips are organized in a certain way and why. And we'll be starting at the power delivery section, which is this area on the left of the board. Let's first have a look at the first relevant chip in the power delivery chain, which is the USB power delivery sync controller. The sync part means that it only syncs current as opposed to being able to deliver or source it. In our case, the source controller is in the wall charger. This controller negotiates 20 volts with the charger and then delivers the current to the next relevant chip, which is this buck converter right here, arguably the most important power supply on the board because it converts 20 volts on its input side to 5 volts on the output. And those 5 volts are then consumed by the remaining 6 power supplies. And when I say power supplies in the context of our PCB, that's a chip that takes a certain voltage and steps it down to whatever is needed by a certain component, or a group of them. For example, this next power supply takes 5 volts and turns them into 3.3 volts. And this power supply on the top right corner takes those 5 volts and turns them into 1 volt, which is then provided to the CPU. And this one provides 1.2 volts for the RAM, and so on and so forth. The next block of components, arguably the most important one, is the CPU and the memories that are all laid around it. On top, we have the memory, which for this prototype run will be 5 2GB chips for a total of 8GB and come with ECC support, which needs its own dedicated chip. Then on the left we have our 64 megabyte NOR flash chip that will hold our bootloader, and finally on the right we have a 32 gigabyte eMMC. And the best part? All these components, so the CPU, RAM, NOR flash and the eMMC, have pin-compatible alternatives, sometimes even from the competition, which means that if we decided to make a light version, like some of you have suggested in my previous video, then we simply take the same PCB and just put 1 gigabyte of RAM chips on, rather than 2, for example, to get a 4 gigabyte version of the board. Or put a 64 gigabyte eMMC chip for more storage. What I'm saying is that the CPU and memories, both volatile and non-volatile, are by far the most determining factor when it comes to the price of the PCB production, and experimenting with a combination of all of those will get us the best price to performance ratio. And speaking of performance, let's talk about networking. In my previous video, I showed you how I can easily get 10 gigabit throughput, but many of you have been outraged, to put it mildly, by the fact that I was using a piece of non-open source proprietary NXP software to achieve that. Well, I have good news for you. I managed to get the same results with net turned on, mind you, using nothing but open source software, namely DPDK and VPP. I'm working on a separate video for that, so be sure to subscribe, because I'm very much looking forward to show you how I got there. Anyway, when it comes to our PCB, this is the area that's dedicated to networking, and compared to other parts, I think it's a fairly simple one, relatively speaking. You got your PHY chips here just under the CPU, then those PHYs are connected to the magnetics that galvanically isolate the PHY chips from the signals that come across the Ethernet cable, and finally the RJ45 connectors themselves. One interesting tidbit about these connectors is that it took me weeks to find these in particular, because as you can see they are low profile, and when mounted on the board their holes are vertically aligned both with the SFP plus cages on the right as well as the vertical USB Type-C connectors on the left. This episode is brought to you by PCBWay. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. It's not quite perfect, but we're using a trick on the enclosure that makes it seem that way, and I'll show you that trick once we reveal the final enclosure. So again, subscribe. Now, unlike our gigabit ports, our SFP plus cages don't need PHY chips because those are usually built into the SFP modules themselves. But what we do need is a chip that's actually a very expensive one and is called a retimer. The primary purpose of a retimer is to condition the signal that travels through it, but in our case we're using it for its secondary purpose, and that's the fact that the interfaces on the CPU and the ones on the SFP modules are not directly electronically compatible. SFP modules use a protocol called SFI, while the CPU uses a protocol called XFI, and as it just so happens, a retimer can also translate between the two, and that's why we use it. And also, while we're talking about it, notice how all the data signals to and from the retimer are shaped differently. The reason for that is a relatively complex one, so let's just say that the alignment of the glass fiber in the PCB substrate can negatively impact the quality of the signal, and it becomes a measurable difference when it comes to high-speed signals. So, in order for our traces not to be aligned with those glass fibers, we make them as round or curved as possible. I know this is a really basic explanation, but because I know I have quite a few electrical engineers among my audience, I'm inviting all of you to do a better job down in the comments, and the explanation that makes the most sense will get pinned to the top. Okay, now before we wrap this PCB overview up, let's talk about the non-port user experience. The first and the only LED you'll be able to see on the outside, when the device is in normal operation that is this RGB LED on the top. It'll shine white, but we specifically chose RGB so that we will be able to convey various bits of debugging information if needed, for example to blink red or blue or any combination of colors or pulsing patterns you can think of. We haven't defined all of them yet, but having an I2C driver connected to the CPU affords us a lot of freedom when we do get there. But this LED is actually not the only one on the board. If we flip it around, there's also 6 pairs of them on the same edge, and it's these that you normally find on the connectors and report things such as connection type for each port and its network activity. We chose to put them there because our device will have a special service hatch that will be magnetically attached to the bottom, which means that you'll be able to easily remove it in order to not only see the LEDs, but also to either install an M.2 card or replace the real-time clock battery. And best of all, everything will be completely toolless because the cover is magnetic and the M.2 latches are spring-loaded and even completely removable. And like I said earlier, for this first batch of prototypes, we don't have the M.2 ports electrically connected to the CPU yet, but we already started working on them for the second round of prototypes. Now that you know how our PCB looks like, let's talk about some facts and logistics around it, beginning with the color and what is called the Stackup. For this initial prototyping phase, we're going to go with your standard green PCB, and the reason for it is the same as why most of them are green in the first place. And that's the fact that traces that are covered with green solder mask are much easier to see with the naked eye, so if we need to break the connection while debugging, which is normally done with a Sharpie, then it's easier to do so. We hope to only have 2 prototype cycles, more on that shortly, and for these 2 cycles we're going to go with green, and once we get to the production run, we're going to go with a matte black. Now, unlike the color, the Stackup is something we cannot change because it's the amount of copper layers on the board, their thickness and types of vias used on the board. We're going with a standard 1.6mm thick PCB and 12 layers, of which 5 layers, including top and bottom, are dedicated to signals. Then we have 2 separate power delivery layers, and finally 5 ground layers that are used as reference planes for the signal layers. We also use all 3 most commonly used type of vias, which are the plated holes on the PCB that carry signals from one layer to another. Through-hole vias are the ones that go through the whole PCB and connect top and bottom layer as well as any other layer in between. Then we have blind vias, which go through either the top or the bottom layer, but not all the way through to the other side. In our case, we just use the ones that go one layer deep, be it from the top down or the bottom up. And finally, we also used buried vias, which you can't see on the board because, as the name suggests, they are buried between layers 2 and 11. Using this approach, so blind and buried vias, does result in a slightly higher manufacturing costs, but it does afford us the possibility to cram this much functionality on a board that is just 12 by 12 centimeters big. Or should I say small? And speaking about manufacturing, we estimate that this will now take about a month before we have our first prototype in our hands, because the PCB production will take around 10 to 14 days, and once done, we get empty boards, so no components on them yet. Then we'll take those boards and deliver them to a local company here in Slovenia that will place all the components on them, and that will take another week or 2, and I'm hoping they will allow me to record the whole process so that I can share it here with you. What follows next is something called the board bring up. You see, the PCBs, once fully manufactured, don't just magically work, even if they're perfectly routed the first time around. What we need to do first is connect them to our JTAG programmer and upload all the necessary firmware and bootloaders. In our case, to the NOR flash chip that's next to the CPU, because that's the first device that the CPU activates and looks into for further instructions on how to boot properly. And this is all assuming that the board is fully functional from the electrical connections perspective, meaning that the schematic based on which the layout was made is flawless. But what if it's not? Well, then we have a problem. And depending on where the bug is, the problem can either be a fairly small and an insignificant one, or a complete deal breaker. Let me give you an example. Let's say our PHY chips are not connected properly and don't work. It is an issue, don't get me wrong, but if that's all that's wrong with the board in the first prototype run, then we can still develop the majority of functionality for everything else and focus on the SFP ports when it comes to networking, while also simultaneously work on fixing the PHY chips. Even if the eMMC chip isn't working, we still have our NOR flash, which yes, is tiny in comparison, but we can still mount an NFS drive to use for the main operating system while developing stuff for the board, or even use NOR flash and build a tiny Linux image that runs completely off of that. But what if our RAM doesn't work? Well, then we have a major problem, because without a functional RAM, the CPU simply won't boot properly. And if the CPU doesn't boot, then we have to find the bug in the first place, fix it, then go through another prototype cycle, costing us at least another extra month. And believe me when I say this, RAM is a bitch to route on the board, because not only does it have more than 150 connections to the CPU, most of them also have to be length matched, which in itself is a fairly complex and involved process. Just look through all those layers and see how many traces go between it and the CPU, and you'll see what I mean. With all that said, here's what the current plan looks like. In about a month from now, so sometime in December, we'll get the first 5 prototypes in our hands, on which we'll attempt to do the board bring up. As a backup, we also ordered components for 5 more prototypes, but those components will stay at the manufacturer for the time being, at least until we're ready to do the second round of prototyping. We do anticipate some bugs in this first round, because I doubt we made it perfect in our first try, but hopefully nothing deal-breaking. And as I said earlier, we still have to route the M.2 ports. If the boards turn out to be usable enough so that they can actually boot, then we flash them with the firmware that we're working on now and start fundraising the next round, which will allow us to enter the certification phase. However, if they do have some significant bugs, then we'll do our best to debug them as quickly as possible and order the next batch of prototypes. Okay, now that you know where we are in terms of development, let's talk about finances. As it currently stands, we have about 5 months of runway left, meaning that the company can survive until March 2025, so it's of the utmost importance for us to get the prototype boards up and running as fast as possible. I'm fairly confident that I would be able to secure another month or 2 worth of financing from our existing investors, should the debugging prove to be more time consuming than anticipated. But I'll do everything in my power to avoid that and deliver working prototypes fast enough to have enough time to present the project to the institutional investors and secure the next round. One way we can also extend that has also presented itself in my last video, in which more than 130 of you have said you'd be willing to deposit $50 to secure your spot for the limited edition development kit, which we plan to release sometime towards the end of first quarter of 2025. First, thank you for the vote of confidence, and second, I haven't had the time yet to consult with our accountants and lawyers as to how to do this right, because there's only one reputation I have and I'm not about to jeopardize it because of some rushed and stupid decision. And speaking about decisions, stupid or not, we still haven't found a suitable name for the device. One idea we entertained was to call it the Ultimate Router, but this would be a tricky one since the word ultimate cannot be registered as a brand. Well, for obvious reasons, because it's a dictionary word. The other idea was to call it Portal, but that also fell through because a networking device with the same name already exists. So it's here where I turn to you. If you have any good ideas for the name of the device, go ahead and write them down in the comments. And if we decide to go with a suggestion that was made by one of you, then that person will get a free development board. But before you do that, here are some pointers. First, it has to roll off the tongue, which means that dashes and numbers should be avoided, unless they make a lot of sense and provide additional context, so to speak. Second, we're looking for a model name, so it has to be future-proof for a possible light version in case we decide to develop it, so it also has to sound good with a light or mini next to the name. Not Air, that one is taken, I think. And finally, a product with the same name can't exist, at least not in the consumer networking space, because that would definitely put us in legal troubles, and obviously we want to avoid that. Now go ahead and knock yourselves out, but before we wrap this video up, I also have to share the best news that's completely unrelated to the router, and that's the fact that Aljaž, my co-founder, got married to his long-term partner. Aljaž, as someone who's been married for quite a while now, let me just say this: let love always prevail. Unshaved but pretty on the inside, signing out.